So let's first define what we mean by being a realist. What I mean when I say I'm a realist is that I believe that there is an exactly understandable way the world is, which is independent of our intervention, independent of our existence, our knowledge. It's possible for everything that happens in nature to give a complete individual description to that process or those events. And then to understand what the causal process is behind those events, to understand exactly what's behind what goes on in a physical process. Now, for reasons which have a lot to do with World War I and a lot to do with philosophy and things that I'm not a scholar of, the predominant view among educated people in Europe in the 1920s and 1930s was not realism. They didn't believe that realism was possible. They thought that science was a way of speaking about our interactions with our interventions in nature. But the concepts that we use, like wave or particle or law or causality or energy, represent our own intuitions and are useful to describe what happens when an atomic system interacts with a measurement device, but do not extend to concepts that stand alone, have meaning when applied just to the atomic system, without the context of the experiment. And I'm trying to talk here the way that Niels Bohr talked, because he was the most radical of these anti-realist thinkers. Let's talk about what it means to be not a realist. What it means to be not a realist is that realism is too ambitious and too hard. We don't have they would say something like, our concepts come from our experience. Our experiences of the world are the big things. We throw them, they bounce back and forth. We play with balls, we sail, we have some intuition about water and wind and so forth. And then we go into the laboratory and we try to take apart an atom and understand what its components are. There are things called electrons and nuclei and protons and neutrons and quarks, but what are these things? And we get very confused when we try to understand what they are. And it is indeed confusing. They're not balls like a baseball or a soccer ball. They're not waves like a breeze kicking up some ripples on a lake. But there's something that to describe them, sometimes we can use the first kind of concept, and sometimes it seems like we need to use the second kind of concept. So they're stretching the limits of what our concepts allow us to describe. So it's natural that some people just get impatient with trying to understand what's really there and trying to invent a concept that fits all the cases of what's really there. And instead says, well, let's lower our ambition, let's just say we're pragmatically describing what happens when we measure and interact with these things. So we don't know what an electron is exactly, but we know that we put it in a certain kind of experiment and we can diffract and measure its wavelength just as if it was a water wave or a sound wave. We put it in another experiment and we can bounce in, measure its energy and momentum. So it seems to be a material particle. And then we wonder, can we contradict ourselves? Again, I'm trying to fake being Niels Bohr, which is hard to do, not just the accent, but his whole way of thinking was, so he was certainly mystifying and mystical in the proper sense of the word of being a mystic. But he was reaching for some accommodation in which concepts were useful, but he didn't claim that the concepts described nature. They described our interaction with nature. And they could contradict each other, because something can't be both a wave and a particle, because a wave is spread out and a particle is localized on a trajectory. So it seems like you're in danger of contradicting yourself. And he said, well, but maybe the situation is so beautiful that there are subtle barriers that prevent you from ever saying it's a wave-like thing and it's a particle-like thing at the same time. Then he said, because he generalized right away, because he saw a bigger applications here. He said, well, when people talk about God's love, then they talk about God's justice the next Sunday. So between God's love and God's justice, there's a contradiction. If God's justice is true and strict, then as a parent, we run into this all the time. How do we be just and loving at the same time? And so Niels Bohr said, maybe there's a general concept to carry these ways, to express the way that these contradictory concepts seem part of the whole. And he called that complementarity. And he proposed that this was a new principle for science, for human life, for religion, for art, for everything. He got quite ambitious, Mr. Bohr. The story that I tell in the book, and that the first two-thirds of the book is built around, is the battle between the realists and the non-realists, or the anti-realists. And in the way that quantum mechanics was textbook formulated in the way that we teach it now, was finalized in 1927, roughly. And that was done along an anti-realist line. But simultaneously, there were a handful of physicists, and these were not quacks, these were good physicists, some of them were Nobel Prize winners or shortly to be, who invented realist alternatives. And one of those that I talk about is what's called the pilot wave theory of Louis de Broglie, who was a Frenchman, which apparently put him socially a little bit in the out-group anyway at this period. And he was wealthy, in fact he was an aristocrat, which also put him out of the social group, so he wasn't really hanging out. And there's a whole lot to say about how that separation let him have an idea that nobody else had, which was an obvious idea. First, an idea that eventually everybody embraced, that the wave-particle paradox, the wave-particle duality, as Einstein called it, applies not just to light, but to electrons, and he was the first person to say that the duality between waves and particles applies to everything, all material particles, as well as radiation and light. And that was accepted, and for that he was given the Nobel Prize. But he went on to say that he could explain the paradox that Bohr wrestled with by saying there are waves and there are particles. Both exist, both are real, the waves propagate and the particles follow the waves. And this is what he called the pilot wave theory, because the waves are guiding or piloting the particles around. And this works. He developed it in the late 20s at the same time as the other theory was developed. It gives all the same predictions and explains at least as much, if not more, than the standard version of quantum mechanics. It was done by somebody who was quite famous through his other work, and yet it was ignored, completely ignored. So there's no textbook, except for a small school of accolades in France and Paris around him. There was virtually nobody who developed his idea. In fact, he even came to disbelieve in it. Everything that ordinary quantum mechanics explains, the pilot wave theory explains. But the reverse is not true, because there's a long list of things that the regular theory does not explain. Regular theory does not explain if you have a radioactive nuclei exactly when it will decay. It just predicts that there's a certain probability per unit time that the atom or the nuclei will decay. But it doesn't tell you why and when it decays, which it chooses some moment, but it doesn't tell you why that moment rather than another moment. If you want to describe an electron and its motion within an atom, the standard theory just says there's a wave function, which is a probability distribution, to find the electron somewhere in the vicinity of the atom, but it doesn't tell you where it is or how it's moving. And if a photon comes and knocks it out of the atom, it doesn't tell you exactly how it absorbed the energy of that photon, how it reacted to it, and how it jumped out of the atom, the it being the electron. The pilot wave theory tells you in detail everything, exactly how, why, and when. So the regular theory is probabilistic. Chance is fundamental, uncertainty is fundamental, statistics is necessary. The pilot wave theory is deterministic, like old-fashioned Newtonian physics. And if you employ it, you can explain everything that happens and exactly how and why and when it happens. So if quantum mechanics is true, that assumption of Bell locality as Bell formulated is false. Then some experimentalists got in the game. So Bell is the 1960s, his theorem is 1964, and by the early 1970s there were some experimentalists who realized they could test this consequence of Bell's theorem in a real experiment. You could make a pair of particles or a pair of photons, let them separate and study their polarizations or their energy or the direction of their flight. You could actually test the principle of locality very directly. And so these were experiments carried out first at Berkeley, I think, and they were muddy and the results weren't reliable, and then at Harvard. Then finally a group of people in Paris led by Despagnat, by, I think we're talking about roughly 1980 now, got definitive results. And the definitive results are that locality is false. This has nothing to do with whether you believe in quantum mechanics or not, nothing to do with anything, because Bell's theorem has nothing in it but a few obvious assumptions, like the probabilities of numbers between 0 and 1. And this one assumption of locality. It's a beautiful theorem in its sparseness. And the experiments together with that theorem tell us that locality is false. That is, there are states of pairs of particles where what the properties of particle B here, over here, turn out to do depend on what you choose to measure or manipulate with particle A. And that's just true about nature. That's the most, if that's not the most crazy, shocking thing you've ever heard in science, I got to repeat everything I just said. In quantum mechanics, there's no explanation of it, it just comes out that way. If you want to have a theory like pilot wave theory that gives a complete description, in other words, if you're not a realist, it's set up so that one of the questions you can't answer is how the information is transferred back and forth. Quantum mechanics is structurally built so you can't get at that question. But pilot wave theory and other alternatives to quantum mechanics that are realistic have to address that question explicitly. They have to show you how the two systems talk to each other. And when they do, yes, they do violate the postulate that nothing can travel faster than light. Is that testable? The answer comes in two parts. At first, no, because these measurements are all random. Just taken, what you measure on this side or what you measure on this side, just taken by themselves, just look like random distributions. So you can't get any information about them, about anything, let alone what's going on over here. So it looks bad for sending information faster than light. But a few physicists, for example, a guy called Anthony Valentini, have speculated that you could throw the pilot wave theory into a kind of phase, like this complex systems people talk about different phases, order and chaotic, and equilibrium and non-equilibrium. He speculates that you can throw the particle wave system into a kind of disordered, far from equilibrium phase, where all of a sudden you can send real signals between the two particles. And he proves that you always have to be able to do that. Although practically we may not be able practically to throw it into a non-equilibrium state. That is a possible state of the system. And that tells you that if you're a realist, then locality is dead, and the idea basically that space is dead. Space is now a discredited concept. And something deeper is going on. Something welds the world together, which has to do with the histories of who talked with who. It doesn't have to do with how far away things are from each other. That logic of that histories telling you who talks to who rather than locality telling you who talks to who is the real lesson here, many of us think.